One of the ideas we had early on was to use the oxygen ilids to repetitively make a whole series of ether rings in what I would call an iterative synthesis. So just like you make a peptide or an oligonucleotide with a small number of reactions repeated again and again and again, we thought it should be possible to build up these polyether regions by, again, using a small number of reactions, and our idea was to use oxonium ylide rearrangement reactions to start out with, let's say, a monocyclic ring and extend that to a polycyclic system, just as you would extend a ladder to a longer length. And the ladder is an appropriate analogy here because there's this class of natural products, many of which were isolated and synthesized here in Japan, known as the ladder toxins, the marine polyether ladder toxins. And this graphic is from the frontispiece of an article that we wrote a few years ago for Chemistry, a European journal. And we decided actually to feature somebody else's chemistry, John Rainier, for this idea of iterative synthesis. But certainly you can do the same thing, we thought, using our chemistry. So here was the basic plan. Start out, let's say, with one pyran ring. And on this ring, next to each other, a benzoic ether and a side chain with a diazoketone. And now when we treat this with a transition metal catalyst, we generate metallocarbene. That reacts with the benzyl ether oxygen. We make an oxonium ylide, and then the benzyl group migrates in a 1-2 shift to give us this product. And now look, we've made a new ether ring fused on to the one we started with. And on this new ring, we have a ketone and a benzyl group. And you can imagine oxidatively converting this benzyl group into a carboxylic acid, reducing and benzylating the ketone, and then converting that carboxylic acid into a new diazoketone, and we would have now a new benzyl ether, a new diazoketone, do it again, and we can put a third ring in. So that was our thought. We were worried. We were worried that this metallocarbene might just do a CH insertion reaction to close a 5-membered ring. That's a very good process for metallocarbenes. We were also worried that there was another oxygen, that this metallocarbene could add to that oxygen instead of this oxygen to give us this 5-membered oxonium ylide. But we thought maybe if we form this ylide doesn't really have any good reactivity options, so maybe this would be a reversible process, and eventually it would drain off through the 6-membered ylide, which can do the 1-2 shift. And once that happens, it's over, it's irreversible. So we made this, and we weren't too surprised to find that with rhodium acetate, we got, as the major product, CH insertion. So this side chain is inserting into the cis CH bond at the neighboring carbon. So it's known that 5-membered rings are very favorable in CH insertion reactions. It's also known that CHs that are next to an ether oxygen are very activated for CH insertion reactions. So I guess this wasn't too much of a surprise. But we did see some of this product, and this is the product we wanted. So we saw this as a hopeful result because we thought rhodium acetate would probably be the worst catalyst for this reaction. Rhodium acetate is particularly good for CH insertions, maybe not so good for forming oxonium ilides. So with great confidence, we went to the copper catalysts, which we had previously studied, and we had shown that in many cases where CH insertion was a serious problem with rhodium acetate, when we went to copper catalysts, we no longer saw that problem. So in particular, we looked at copper hexafluoroacac, which is generally our best catalyst for this oxonium ylide chemistry. And you can imagine we were very surprised when instead of this product, we got out this dimer as our only product, a type of product that's formally possible with metallocarbenes, but that we almost never see when we have other options like ylid formation. That was pretty disappointing, I can tell you. The guy who did that reaction, Fred Marmsetter, was pretty upset when it happened, but we continued to look at it after thinking about why this might have happened. So remember I said, well, maybe we might form this 5-membered oxonium ylid, but I said that's probably no problem because this ylid can't do anything. It'll revert back to the metallocarbene and eventually give us the product of the 6-membered ylid. That was our idea. Clearly that's not happening. So we thought maybe this ylid is more of a problem than we thought. Maybe this ylid, if it accumulates, can react with, let's say, another molecule of starting material to give this apparent dimeric product. And in fact, maybe our problem is, to the extent that we're forming this ylid, maybe this one actually is in equilibrium back to the 5-membered ylid because the 1-2 shift is too slow. Remember I told you the mechanism of a 1-2 shift is stepwise, involving an initial homolytic cleavage of a carbon-oxygen bond. That actually has a fairly high activation barrier. And so you can imagine that this might be slow enough that this ylid could drain off through an alternative process. If that's really the case, we thought maybe we could speed up that process by going to a different mechanism. Let's go to the 2-3 shift instead of the 1-2 shift. The 2-3 shift is a concerted reaction. It has a much lower activation barrier, we would assume. So we made the corresponding compound with the allyl ether instead of the benzyl ether. And in this case, with rhodium acetate, we saw a very similar result. Roughly equal amounts of these two diastereomers, both of which came from the 6-membered oxonium ylid, and the same CH insertion product. That shouldn't be C2H5. It should be C3H7, I guess. Well, 1, 2, 3, no, C3H5, yeah. Anyway, we went to the copper catalyst, and in particular now this one, copper trifluoroacac, gave us a very nice result. Only 5% of the CH insertion, 75% of a combined mixture of these two diastereomers, with the axial diastereomer greatly predominating, 73-2. We actually want this one in order to have the correct stereochemistry to build up the polycyclic ring, but you'll recognize that it should be possible to interconvert between these two epimers, because this is the only point of difference, and we have a ketone right next door, so we should be able to epimerize at this position. As to why with copper catalysts we get mainly the axial isomer, we have some speculation, but in the interests of time, I'm not going to walk you through this. We can talk about this afterwards if anybody has any questions.